my name is Akila, and this is my Lab 5 Falling Slinky. So for our introduction, we have the purpose of this lab, which is to predict the motion of a falling slinky and analyze the effects of its surroundings. The goal is to determine whether the bottom of the slinky stays stationary in the model. For this lab, we have three fundamental physics principles: Newton's second law, drag force, and the gravitational/slinky force. The main result of this lab was that although there are some fluctuations, the bottom of the slinky remains stationary, and the system and the surroundings of this lab, for the system we have the slinky and the surroundings would be air and the earth/gravity. So for the observed motion part of the lab, I used tracker software to track the position of the slinky. The mass of the slinky was 0.218 kilograms. Derek's height from when he dropped the slinky was 1.75 meters. And then here you can see the initial position, and the initial velocity was 0. So for the computational model, I inserted my initial conditions into my code. So you can see we have the same slinky mass of 0.218 kilograms, and I put the initial position and initial velocity into my code, and then here I have B equals 75, where B is the drag proportionality constant. So for my first while loop, we have the time when the bottom of the slinky is constant, which is 5.53 seconds, and then the gravitational force can be seen in line 71, along with the slinky/tension force in line 72. Then in line 77 we have the velocity update, and in line 79 we have the position update. So then for the second while loop, we have the time until the slinky reaches the ground, which is 8.13 seconds. And then to calculate the net force, we use the gravitational force, which is seen in line 108, as well as the drag force, which is in line 109. And once again, we're also going to use the velocity update formula as well as the position update formula. So the results of this experiment, we have the observed versus predicted position of the bottom of the slinky. The predicted is represented by the blue line, while the observed is represented by the orange line. So as you can see by looking at the graph, both graphs have the same general trend. They both observed and predicted the bottom of the slinky to remain stationary initially, and then they accelerated downward after around 6 seconds. Some differences were that there are fluctuations. The observed data has minor fluctuations in the flat region before 6 seconds, while the predicted graph remains perfectly constant during this time. These differences are likely due to real-world imperfections such as air resistance, slinky deformation, or timing inaccuracies in measurements. And some possible errors are observed motion experiences, fluctuations due to external forces not accounted by the model, and inaccurate tracking point placement on the tracker, so basically human error. So for our discussion, we want to know, why does the bottom of the slinky remain stationary? The force in the y direction cancels out. Although the gravitational force acts downward, the slinky acts as a big spring and counteracts the force with a tension force of equal and opposite magnitude. What if we put a large weight at the bottom? Would it remain stationary? It depends. As long as we have a slinky that is either long enough or has a large enough spring constant so that tension equals gravitational, the weight will remain stationary until the top of the spring reaches it. So in conclusion, the results of the lab demonstrate that the predicted motion of the bottom of the slinky closely matches the observed data. Both the predicted and observed graphs show that the bottom of the slinky remains stationary during the initial phase until the top collapses, after which the bottom accelerates downward. This behavior confirms the unique falling motion of a slinky, where tension within the coils keeps the bottom stationary until the collapse wave reaches it. The small deviations between the observed and predicted data, such as the minor lag and fluctuations, can be attributed to experimental factors like air resistance, measurement inaccuracies, or variations in slinky deformation. Despite these discrepancies, the overall alignment between the two datasets validates the theoretical model for the falling motion of the slinky. This experiment highlights how physics models can effectively predict complex real-world behavior with a high degree of accuracy.